Electromagnetic induction. We are going to see about the lesson electromagnetic induction. Electromagnetic induction was first discovered by Michael Faraday. We already know that Christina Oyster discovered that steady current produces steady magnetic field in a circuit. Many physicians use this experiment with a converse effect. One of the physicians was the Michael Faraday. Faraday discovered the electromagnetic induction. He used an experiment by using a solenoid which was connected with a battery and with a key. Now he made a closed loop to the solenoid. Now he considered loop 2 and loop 1. Loop 2 is considered as the loop is around the solenoid wire. The loop 2 is around the solenoid wire. Solenoid. And loop 1 is in the part of the solenoid. It was not connected, but it's the part of the solenoid. So the loop 1 is considered to be the part of the solenoid. Now he closed the key. The current is flowed in this direction. Due to this current, there will be a magnetic field. So the magnetic field lines which is opposite to the direction of the current. Now in the loop 1 there was a magnetic field as well as current. The loop 1 has both magnetic field as well as current, but in the loop 1 there is no current is flown in the loop 2. But there was magnetic field lines was produced in the loop 2, but no current is flowed through the loop 2. Then after a few days, Faraday discovered that when the key was open, the loop 2 has both magnetic field and the current I. The loop 2 has magnetic field and also current I. When the Faraday closed the key, there is no change in the current as well as the magnetic field. Then Faraday discovered and understood that not the steady magnetic field produces steady current, but change in magnetic field. Change in magnetic field produces current. He also used another experiment by using a galvanometer. Now Faraday take an experiment using a galvanometer. This is the galvanometer. There is a DC moving coil. This one is minus, and this one is plus. I connected a copper wire. This copper wire is said to be a solenoid. There are n number of turns in this solenoid, and I was fixing it in the upside of the galvanometer. Now one of the end of the wire is connected with the minus and the other end is connected with the plus. Now using a magnet, I'm going to show the deflection in the galvanometer. This deflection is due to the current produced due to the change in magnetic field due to the magnet. So now let's see. This point is said to be the North Pole, and this point is North Pole, and this is South Pole. The white color point is indicate the South Pole, and a non point is said to, and this point is said to be the North Pole. When I keep the North Pole is not moving here, so there is no deflection. There is no deflection in the galvanometer. When I put the magnet inside this solenoid, the galvanometer shows a deflection in the right side. Now let's see. As you see, the galvanometer shows a deflection at the right side, and now when I take the magnet upward, it will shows a deflection at the left side. Let's see. So now the deflection has been at the left side. When did you notice that when the magnet was inside the solenoid, there is no deflection in the galvanometer. This indicates that when the magnet was in rest, there is no current produced in it. This means change in magnetic field produces the current. When I put inside the bar magnet, it shows the deflection in this side. When I take it out, it was in this side. When it is in the rest, there is no deflection in the galvanometer. It was in rest, and the galvanometer also in rest, there is no deflection. If I take the converse part, I put the north side inside the solenoid. If I put the south side into the solenoid, the deflection will be changed. Let's see. I am putting the south side into the solenoid, and then the galvanometer shows a deflection in left side. The galvanometer shows a deflection in left side. Let's see. So as you see, it shows a deflection in left side, and it was in rest, so the galvanometer shows no deflection. And when I take it out, it shows a deflection at the right side. So the poles indicates the difference in the direction of the current. At the north pole, it shows a different direction of current, and at the south pole, there is a different direction of current. This was introduced by the Lenz's law. Let's see the experiment again. Let's see this experiment again. Now this point, the white color point indicates the south pole, and there is nothing in here. This is indicate the north pole. When I keep the north pole, I'm going to use this north pole inside and outside the inside the solenoid, so that there will be a deflection in the galvanometer. Let's see how this north pole induce this current in the solenoid. When I took it inside, when I take it outside, and let's see in the south pole. So when I took it inside and it outside, you can see the difference between them. When I use the north pole, when it goes inside, it shows the deflection in the right side. When I take outside, it shows the deflection in left side. But in controversy, for the south pole, it's just opposite to the north pole. When I put the south pole inside the solenoid, it shows deflection in the right side. When I take it out, it shows the deflection in the right side. So this is the difference between the north and south pole. This is due to the direction of the current. The direction of the current changes when the poles are changed. Let's see it in detail. When I put the north pole towards the solenoid, I mean it's inside the solenoid. The deflection shows in the galvanometer is in right side. When it was in the inside, it was at the rest in inside like this, and there is no deflection. There is no deflection in it. And when I take it outside, the deflection shows at the left side. So that's the controversy of the South Pole. When I put the South Pole inside the solenoid, towards the solenoid, it shows at the left side deflection, and when was it rest, it was inside the solenoid, it shows no deflection, and when I take it out, it shows a right side deflection. So you can see that North Pole and South Pole shows a different deflections. This was found out by the Faraday. Faraday's main point is to explain that change in magnetic field produces the current. The deflection shows that the current is flown through the solenoid. This means that change in magnetic field produces the current. When the magnet is in a stationary, there is no deflection at the galvanometer. This means steady magnetic field, that is no change in magnetic field, means there is no current produced in the solenoid. So this was the Faraday's experiment. Let's see the next experiment. Let's see the next experiment of the Faraday in the next video. Thank you for watching my video, and also see the next video of the Faraday experiment. Thank you.